Hello everyone, welcome to another Stat385 video. So last time we covered atomic vectors where each of the elements is the exact same type. So say something like this, where we have numeric type, or in this case double. And then we discussed the natural coercion that occurs. So if I were to have a double and then a logical, here it would convert the logical to double. And if I added a character, it would, let's see what's a good one, character. It would convert everything to character, just to make sure. Okay, so these atomic vectors are, generally speaking, when something is given the name atomic, it's like the most basic thing that you could do in whatever you're studying, and that's the case here. Atomic is the building block of objects in R, and now we are going to discuss something called a list, which is a generic vector. Okay, so I'll take this thing right here. Actually, I don't need type of. Okay, and instead of doing, so here I had this coercion. Now I'm going to change the combine function to list. Okay, so here, what's printed out is a little bit different. We have a double bracket notation listing the elements of the list. So it's a list of 3 objects. Each of the objects is just a length 1 object. Here, though, it's a length 1 object of different types. So here in the print statement before, okay, so if I change list back to combine, it coerced everything into type character. Now on the list, what's printed out, each of the objects is separately its own atomic structure, because I only have a length 1 object, so there's no coercion within each one of these objects populating this list. It's just the number 42, the logical statement true, and the character vector character. Okay, right. So what is the type of a list? It is just list. Oops, what did I do? Oh, okay, I see. Type, wait, what? Type of, should just say, oh, okay, that's right. I had a parenthesis gone wild. Okay, type of list. Okay, so, right, if I want to, take out a particular object, this is kind of getting ahead of the game, I could extract it and then investigate the type. So here the second element of the list is an object of type character. Okay, that's getting kind of ahead of the game though. Okay, right, so, okay, I can still use our combine function. So say I have actually, let's do a basic list of 1 element, just 1, object 1. I can combine a single object 1 to a list, and what that's going to do is it's just going to make the entire thing a list. Okay, so here, just to be a little bit, okay, so here the first element of the list is 2, the second element is 1, but it just, once you have these atomic vectors on the outside, it's just going to combine them to be a list if one of the elements is a list that's being combined. Let's just do this real quick. Oh, so it's actually going to take, if I have an atomic vector, it's going to extract each one of the elements and then combine it and then make a master list of 4 elements. Okay, cool. All right, so, so going back to our basic list with mixed types, we can see again this this double bracket notation here. So so the list is, there's 3 objects that you can see, and then this double bracket notation expresses the object number, the position of the object in it, and then below it is the object itself. Here nothing is very fancy, but you can see now there's 2 types of subsetting, which we're going to get into subsetting in the next video, but there's 2 types of subsetting at play. One is the object position in the list, and then within each particular object, positions of elements inside of it. Okay, and like atomic vectors, we can give, right here everything's unnamed. I could name things and do a named list. Okay. And so now it changes things slightly, very similar to what we saw in atomic vectors. But here I made the first object I assigned it the name A, second object B, third object C. And then when I print it out, you can see instead of the double bracket notation, now I have a $sign and then a name, which I've given it, and then the object is then displayed. Okay, fairly simple. Okay, so now let's create a few objects and assign them names, and to continue to discuss from here. Okay, so I'm going to create a basic list. You know what? I'm just going to take this. All right. So I'm going to take what I have, assign it the name foo. Now let's do A equals 1 to 10. So double vector 1 to 10. B is character vector. Hello world. All right. C is a function. And then D is a list. A equals 1, B equals Z. Okay. Okay, and you can see that when I run these, they now appear in the global environment. All right, and we'll do one more. 4, 3, 2, 1. Okay, oops, sorry. I want this. No. We'll have it be an atomic vector for demonstration. All right, so as before, I can take a list, assign it the name, then I print it out. This is what we've seen before. List of 3 elements, and we can see each of the objects printed out. Okay, bar is slightly different. So now it's getting a little bit more realistic. Okay, so now we have a named list. And now you can see here, the first object isn't just a length 1 vector. It's a length 10 atomic vector. Then object B is this character vector. Object C is a function. This is just what prints out for the log function. And then object D is itself a list. And if you track it, it's a named list. So let's see here. Okay, so I had the first element is 1. I give it the name A. The second object is a character vector, Z, length 1 character vector. I give it the name B. So this is all stored inside of this other list, given the name bar, in object or an element named D. Okay, so here in element D of the list given the name bar, I have a list with 2 objects. First one is given the name A, second one given the name B, and here are the objects themselves. Okay, so list within a list. But you can see here the big picture takeaway is that when I have a list, they're very general in what they can store. They can store numeric vectors, mixed type vectors, but including lists themselves. And lists this isn't just like a pedantic exercise. This is like when you do things in statistics, say fit a linear model using R, you can see here that when you go to the help page, the value, it's an object of class LM, is a list containing at least the following components. So it's a bunch of stuff, but some of them are useful for displaying summary information about a model fit, whatever. So the point being here is that when you fit a linear model, which is a really basic thing you do in statistics, the output is itself a list with a bunch of things, and then when you call functions on it, then you can perform statistical analysis. So this general generic vector construction within R is extremely useful it's general in what it can store, but it's extremely useful in statistics and just, data science and beyond. Okay, cool. Sorry, it's getting a little bit ahead, I would say. This is not a statistical analysis class, it's a statistical programming class, but nonetheless, it's very useful to see how these things connect. Okay, moving on. So, if I ever get stuck, I can check to see if, what the objects are that I'm creating. Is that vector bar? Okay. All right. Okay, so everything is a vector. Cool. However, not everything is an atomic vector. Oops. Okay. Man, I cannot type. Oh, I see. Being very silly here. Okay. Right, so generic vectors and atomic vectors are themselves both vectors. However, you can see here that the generic vectors themselves are not atomic vectors. Okay. Expected, but nonetheless, nice to be able to see. Similarly, I can check to see what is a list and what isn't. Okay, so if I just do that, is.list, is.list, is.list. Okay, right. Okay, cool. Another thing too is, and this is something that actually does create a lot of confusion for, I would say, even experienced R users, not just beginners, is what is a length of a generic vector. So, right, if I go to Baz, first of all, okay, where's Baz? Baz is this thing. I'm going to add spaces. Okay, so Baz, as you can tell, is this atomic numeric vector. Okay, I take this length 4 atomic numeric vector, assign it the name Baz, and if I just type that into length, it's just what we've seen before. It's a vector of 4 elements. Great. So now what is, say, the length of this object, the list foo? Okay, I think this is pretty simple because either way you think about it, it's going to be length 3. Like there's only 3 objects specified, and each of the objects is length 1, so pretty simple. Okay, so now what is the length of bar? Okay, so there's a few different ways to think about it. The total number of objects that is contained in the list itself, or the position of all of the different objects inside the list, like each of the objects separately. So how many objects are there assigned, like given placement in the given names in say bar, versus how many objects are there within each of the objects of, or how many elements are there within each of the objects of the list. R picks the first one. The length of the list is the number of elements separated by a comma, or given a name. So length for this list is 4 elements. And if you want to then go deeper into each one of these particular elements in this list, then you can. That's going to involve subsetting. I guess we'll just do it really quick. So let's display bar. Okay, if I just do, we're getting a little bit ahead here, but this is the object given the name, assigned the name A, which is an atomic vector length 10. And if I hit length on that, then it should be 10. Yes, okay, good. But the length of the list itself is 4. There's 4 objects. Okay, so sometimes printing out an entire list is a bit unwieldy. So here, yeah, if this is the amount of console space I want, I have to scroll up. It also doesn't present a complete account of all the information. And what I mean is it doesn't tell you about the different types of the objects that are inside this list. So there's this command called structure, str, and it will give you a more concise and detailed description. So here you can say structure bar. It's a list of 4 objects. Well, just cut off the word objects, but list of 4. And then here are the objects themselves. And you can see integer, there's 1 through 10. Let's do something. Okay, you know what? Just to check it, let's change 1 to 10 to 1 to 100 and see what happens. So again, I'm taking the same list and I'm assigning it the name bar. I'm gonna overwrite the bar that existed in the global environment and just change it slightly. Okay, so now when I do that, and now I call structure on bar. Aha, it tells you how many elements there are in this, integer vector. My bad, did I say double? That's right, when you do colons, it's integer. And then it displays the first 10 and it has a ... for there are more. Okay, cool. Also in the global environment over here, bar, if I just this is the same thing. It's the structure. So you could access this by looking over in this pane over here as well. Okay, same here, cool. Baz is just displayed. Okay, awesome. Let me go back to this, cool. All right, structure, cool. All right. Right, and it tells you that, okay, so first element integer, second element character. There it is. It's not too long. You can display all the elements of that character vector. Second one is C is a function, and there's what it looks like. And then D is a list of 2. So bar is a list of 4. D is a list of 2. A numeric 1. B character Z. Cool, awesome. All right, you could also view bar. I don't think that is all that useful, considering we can do it over here and just call structure. However, view will be useful later in this video when we discuss data frames. Okay, sometimes, actually, I use this quite a bit. You can, you can force a list to be an atomic vector. So I could take my list. Okay, where's foo? Foo is a list of 3 elements: numeric, logical, character. So I could just unlist that, and now it's an atomic vector, but it did coercion. Similarly, what happens if I do that? Oh, that's not good. That's not fun. Okay, so so let's see. When would I want to actually do something like this? If I had list 1 through 10, 11 through 20. So I have, actually, let's print it out, see what that looks like. Right, so first object of the list is atomic vector 1 through 10. Second object of the list is atomic vector 11 through 20. And if I unlist, it'll be one long atomic vector. So although I'm not telling you a case where this is useful in some statistical analysis, you can kind of see that this is more realistic than unlisting the elements of bar. Okay. Extracting elements of a list. We'll get into this in a little bit more detail when we do subsetting, but nonetheless. So if I look at, recalling that Baz is a double vector, if I were to, I could just pull the second element out. I could also use this double bracket notation similar to a list. And here, type of Baz is also double. Okay, so if I do the same thing for foo, what happens? So this will pull the second object out. that's not let's try it for bar. Let's do the first one. Right, so that pulls the first object out of bar, which is this atomic integer vector, numbers 1 through 10. Okay, cool. Now, if I use the single bracket, which is more familiar for atomic vectors, it's slightly different. What it does is this will pull the first object of the list, but preserve the list structure. So you can see here the difference is that I'm accessing the first element of this list, but it'll say, okay, first element is the name A, and then here is that object. Sorry, I'm pulling out the first object of the list, and then here is that object in full detail, but preserving the list structure. When you do the double bracket notation, it's going a step further by extracting the object out itself of the list structure to then be used. So like, what happens if I do mean? Right, it doesn't work because it's preserved the list structure. Type of, this is a list. This is an integer vector. Right, okay, so we'll get into it in more detail. With bar, I have names. So I can just pull the objects out by referencing their names. Cool. What happens if I do this? Same type of thing. Single versus double bracket notation. Interesting. Okay. Oh, this is kind of cool. You could, if I do bar C, that's a function. This is pretty nifty. You could then, this is pretty tricky. So this is just an atomic vector of elements 1, 2, 3, right? This is a function. It's the log, right? It's the log function. So then this will take the log function out and then we'll evaluate it on this vector doing vectorization. Very cool. All right, that's fancy. All right, so now, okay, so we've done atomic vectors, we've done generic vectors. So now let's get into this will be still a generic vector, still a list, but it's one that's going to be extraordinarily useful for data analysis, statistics, visualization, all that kind of stuff, data science in general. Okay, so I'm gonna pull some code. All right, so this is a list, 4 elements, or 4 objects. Each object now has a particular constraint. Each object is the same length. So objects given the name A is integer vector 5 decreasing to 1. Object B is the character vector A 5 times. Object C, logical 5, length 5, and D is just 1 repeating. Okay, so if I run this code, it'll just display a list as we've seen before, named list. Each of these objects is given a name inside the list. Okay, so here, nothing special. We've seen this. However, I can take this list and change it to data.frame. I change list to data.frame. That's it. And what's going to happen? Now it's printed out something different. It's printed out what looks like a matrix. Now, the matrix is a very specific type of displaying like an atomic type structure. This is more general than like a matrix in R. What I mean by a matrix is just it has has a number of rows, number of columns, and it, each one of the columns has the same length. Okay, I don't want to confuse it with a matrix in R, but nonetheless, there's 5 rows, 4 columns. In statistics, data science, this would correspond to the rows being individuals, columns being what is recorded on each one of the individuals. Here the columns are given names, and then what is displayed is measurements on individuals to be used. And here the measurements can be different types, right? Like we could have numeric measurements. We could have, qualitative, like factor type variables, logical things. Did something happen to an individual? Typically you wouldn't have just like repeats of ones, but that could be a model, or like an intercept in a linear model or something, whatever. But regardless, we now have a data frame, and I'm gonna give it a name. I typically, when I'm doing demonstration purposes, I use the name dat. I don't want to use the name data, because data, as you can see, is a reserved thing in R, and I don't want to mess with that. So dat. Okay. Some people use df, same thing. That's a distribution function for an f distribution. Don't want to do that. So you could either go with foo, or I could either go with foo or dat. In this case, I'm going to pick dat. Whatever name for just something that you want to use, where you're demonstrating or you're playing around, and you're not going to give it a full descriptive name. You can pick whatever you want. I'm choosing dat. Okay, so I have a data frame. I'm assigning it the name dat. Here it is. I can print it out. It's the same that we saw before. I don't use attributes too much, but you can see the information on this data frame. It has elements with the names A, B, C, D. Objects with the names A, B, C, D. These are columns. They're also objects of a list, which we have not seen yet. Class, which we'll get into later. Class data frame, and it displays row names 1, 2, 3, 4, 5. Cool. Right. Names dat. Those are the column names, but thinking more generally within what we've built so far, these are the names of the objects inside of the list. Okay, row names. Oops, my bad. Row names. Right, just 1, 2, 3, 4, 5. Call names, A, B, C, D. Names and call names is exactly the same. Okay, cool. All right, and then interestingly, although already stated, a data frame is a list. And what does that mean? I know that we're going to do subsetting in more detail. I can pull objects out using the same type of thing that I would do for a list. Oh, that's interesting. That's slightly different. Okay, so what happened here? So because it's a data frame, it's treating the second object as a column vector, not as like a row vector. That's actually quite interesting. Just out of curiosity, is it a list? It should be, right? Okay, cool. Awesome. All right. As before, we can, extract a useful description of what is contained in this data frame using structure. So here, interestingly, cool. It says 5 observations of 4 variables. This is definitely using statistical type, terminology to describe the elements of this this object. But it's still a list, so it gives the names just in the same way that we saw before when we called structure on a list, particularly that was bar. We can see that the object A, integer vector 5, 4, 3, 2, 1, B, character, C, logical, D, numeric. Cool. Now though, the view command, before it just displayed, let's pull it up again. So when I view bar, it's not really that useful, the viewer, but here it's now useful. This is actually kind of cool too, because you can sort things. What does this do? Oh, all right, cool. So if you have a big data set or a bigger data set than this one, then view could be useful. I use it quite a bit. My students use it quite a bit. It's nice. Right, like atomic vectors, you can do some recycling. So let's do this. Take this one out. All right, and let's do that. Okay, so everything up here is length 5. And the last element is just 1. Okay, so it's going to fill it in. What happens if I do this? So now the recycling, it's 1, 2, 1, 2, 1, 2. Complains. Yep. Will it store anything? No, it's an error message, right? Not a warning. Doesn't work. So if you're doing recycling, you have to make sure that the dimensions line that the dimensions line up. Okay. Right. Let's get that off the screen. Okay. So length. Any guesses? Is it going to be 5 or is it going to be 4? Is it going to be 5 observations or is it going to be 4 columns, 4 objects? It's going to be 4 objects. Right, so remember, data frames are lists. The columns themselves are the objects of that list. Right, so here is data frame. I can swap out the word data.frame for list and I'm back to a list. So it's the same type of, internally under the hood. It's operating, since we already know that data frame is a list, it's operating as a list. And so here, the length of the data frame is the number of objects in the list. The objects are given by the columns in the data frame. Okay. However, we can do, if we want, but now thinking, even though it's still a list, thinking of it as a data frame, we can look at the number of rows and the number of columns. So 5 rows, 4 columns, or the total dimensions if you like. I use these quite a bit. They're actually quite useful. Okay, cool. Let's see if I do data.frame a equals 1. This is rather silly. But you have to give things unique names, or else R will manually change them. So something to be mindful of. Okay, so I think that we can stop here. Thank you for your attention, and we will get into, although I've done a little bit of it, we'll get into subsetting in more detail in the next video. All right, thank you for your attention, and take care, and see you next time. All right, bye.